Hey everybody, welcome back. Here we go into chapter 16. So I'm hoping that you've had a chance to look at the chapter 15 note on static electricity. Really, there's only the one thing that you need to take out of chapter 15 that you're going to need throughout the next chapters, and those would be the formula for quantity of electric charge, Q equals NE, where quantity of charge is equal to N, the number of surplus protons or electrons, times E, the elementary charge, or the charge on one electron, which is 1.602 times 10 to the negative 19 coulombs. Right, so that's really the only thing that I think we really need to get out of chapter 15. So we're going to move into chapter 16 and start doing a little bit of math and then get into some circuits. And then we're going to bring magnetism in towards the end. All right, so we're looking at probably 2 good weeks to get through this unit. It's a fun unit. There's lots of applications. If you kind of get into the math, do all the practices, we're working through it, you'll find that, I don't know, I like electricity and magnetism. Okay, so chapter 15 was about building up static charge on an object, and it's being parked there, stationnement, stationary or static electricity. Chapter 16 talks about current electricity. When I think about current, I think about a river, and I think about something flowing. In this case, electricity, by definition, is a short form for electrical potential energy. Because of that, it is measured in joules because it's energy. We usually use EE for our symbol for electrical potential energy, just like EK for kinetic and EG for gravitational. And just like gravitational energy, it is stored energy. So electrons, I'm just going to use an example here. Electrons will pick up energy at Niagara Falls at the Suratum-Beck hydroelectric generating station, and then they're going to carry those electrons from Niagara Falls into my house here. Right, so they are carrying that electrons, that energy. They have it stored up in them, and they're going to move it along with them until they get to a place where they can deposit that energy or give that energy away. So electrical potential energy is stored energy, right? It's potential energy that is stored up, in electrons that are moving. Now, when I look at the whole process here, again, we're looking at what's going on with our electrons here. So I know that where do the electrons, if they're going to gain electricity, gain energy in order to bring it to my house, I'm going to recognize that they're going to gain energy basically by transforming it from another type of energy. Right? So remember, energy transformations happen all the time because of the law of thermodynamics. We know that anytime energy leaves one form, it has to be converted into another form. Right, so energy cannot be created or destroyed. Right, that's our first law of thermodynamics. And what happens is electrons will gain their energy from other forms of energy at some type of electricity generating station or a power plant. Then what's going to happen is that energy, if you watch the video for nuclear power, first part is making the energy for the electrons or harvesting or collecting energy for the electrons. Then the electrons are going to bring them where they're going to go. And then the last part is the electrons are going to give their energy to something, whether it's a laptop charger, a cell phone charger, a light bulb, a toaster. Right? They're going to give their energy to some other device that we call a load. And that load will take the energy from the electrons and convert it into another form of energy that can be used to do something. All right, so there's the 3 things that we're going to be talking about. Is one, how electrons will gain energy. Not so much. We've talked quite a bit about that in our nuclear energy unit. You looked at hydroelectric power also, and we're not going to talk about solar or wind, but just recognize there are other forms of energy available for donating electrical energy to electrons. So when we're transporting and delivering energy throughout Ontario here, right, the middle part, we've got the electric grid, which basically connects the power station with my house, the power station with your house, the power station with the school, the power station with everything in Ontario is connected to the power plant. But then recognize that if the power plant's connected to me, but it's also connected to you, then I guess I have to be connected to you. So it turns out that the grid connects all users of electricity in the province and beyond, because we actually sell surplus energy that we make here in Ontario to New York State, and whenever we have more electricity than we need, then we will sell it to other people who will be needing that energy. Okay, now we've already talked a lot about efficiency in this course, efficiency of energy conversions. Really talks about how much waste there is when an energy transformation goes on, how much of it gets converted into the desired final form of energy, right? And as we're looking at the efficiency of energy conversions, we're going to recognize that it impacts on a lot of different things. Number one, on the planet. Number two, also on our wallets, right? And how much money that we have to pay for our electricity. So devices that don't waste a lot of energy are very desirable because I can have the least amount of energy going out the window, right? Being wasted. Okay, so 19.2 in the textbook talks about electric current. Electric current, again, is the flow. Think about something, a current is something moving, like water flowing in a river, but in this case, it's the rate of electron flow. Now, if I say a river has a fast current, it means the water is moving really fast. If a river has no current, like it's been dammed, then it has no flow. So the rate of electron flow talks about this quantity that we call electric current. The symbol for current is I. I'm not sure why it's I. Probably comes back to a Latin or a Greek word that talks about flow. Because we're talking about the rate of something moving, speed of something moving. If I'm talking about how fast water's flowing in the Niagara River, I'll typically talk about, say, how many liters or thousands of liters go over the falls per second. Right? We do the same thing with electric current. We don't measure their speed in a quantity of how far they move per unit of time. We actually talk about how much of the electrons pass a point in a unit of time. Right? How much pass a point in a circuit in a unit of time. Now, to measure the quantity of charge, we're going to use the quantities that we used in chapter 15, which are coulombs, right, named after Coulomb, of charge, measured how many coulombs pass by a specific point per second. And if 1 coulomb goes past per second, we say that the speed or the current has a rate of 1 amp. 1 ampere, named after Henri Ampere. And the short form for the symbol is, or for this unit, is a capital A. So A's talk about how many electrons pass a point per unit time. So as with any rate, the formula is going to have time in the denominator, and the current here, I, is going to be determined by dividing the amount of charge, Q, that passes a point in a fixed amount of time. Right, so I is the current in amps. Q is the quantity of electric charge in coulombs. How many coulombs have gone past a point in how long were we monitoring it? So we know from chapter 15 that we can use Q equals NE to calculate the Q that we're going to use up in here, right, where N is the number of electrons or charges and E is the elementary charge, 1.602 times 10 to the negative 19th coulombs. Because it's a charge on an electron, it's also the charge on a proton. Right? We often neglect to say that when we're saying, oh, E, the elementary charge, is the charge on an electron. Well, it is, but it's also the charge on a proton. Okay, so if we keep on going down here, we typically measure current by using an ammeter. So if I've got a circuit, so I'm just going to draw a circuit here, a very simple one. Put a bulb in here. And the bulb is on. Okay, now if I want to know how fast the electrons are moving through that circuit, I can, oops, I didn't want to do that. I can stick an ammeter there along that piece of wire and say how fast would the electrons be moving past this ammeter as they're moving through the circuit. Okay, so that's how we measure an ammeter. We measure it in series. I don't know if you remember that word series from grade 9, but a circuit that's in series means electrons only have one path, right? So electrons that leave the battery here, or the cell, they're traveling around the circuit and they're returning back to the cell again, right? Electrons only have one path. They have to go through the ammeter. I didn't give the ammeter connected to 2 points outside of the circuit. I actually embedded it within the circuit. Okay, and that's called a series circuit. Now, we're going to talk about series and parallel circuits again when we come back to this. So, one of the things about electric circuits is really all the way along that path, right? All the way along the path here are electrons in my circuit. If it's turned off, right, if I could take the wire off the battery, all those electrons are there in the wire. And as soon as I connect that wire and push it back onto the battery again, electrons start moving. Now the way they move is electrons from this very first part of the battery will get pushed into the wire because they're getting pushed away from the negative charge that's present here in the battery. Now notice that there's electrons all the way through this circuit here. Electrons are negative. Electrons are being pulled towards the positive terminal. So this is the positive terminal of my battery, and this is the negative terminal of my battery. So as electrons leave the negative terminal, they're being pushed away. At the opposite end of my circuit, electrons are being pulled towards the positive because opposites attract. And along the way, as the electrons leave this end, they will push the ones in front of them forward and through the circuit. So as water comes out this end, as electrons come out this end, they push one out that end. As another one gets pushed in this end, it pushes another one out this end. So it's kind of like water in the hose. If you turn the hose on, the first water that comes out of the hose, if the hose is full, right, from one end to the other, as soon as you turn the hose on, right, the first water that goes into the hose coming out of the tap is not going to be the first water that comes out the other end. It's not going to come out the end until all the water that's ahead of it has been pushed out. Right, and that's how we have to think about electrons. Electrons are particles here. They're solid particles that are going to behave like solid particles. So, whatever speed they come out of the battery at on this side will be the same speed or current that they leave the circuit on this side. And it will also be the same speed that they went through here, and the same speed that they flow through the bulb, and the same speed. So it doesn't matter where I put my ammeter in the circuit. I stuck it down here. But if I stuck it over here, it's going to read the same thing, because the speed is going to be the same everywhere in the circuit. If I put it here right beside the bulb, it's going to be the same. So again, try to visualize the electrons moving in the circuit here. So at the end of the day, the current as it leaves the source, so again, remember our source is where the electrons are coming from, is going to be equal to the current, there should be an equals sign there, equals the current returning to the source at the other end. Right? However fast they're coming out of this end will be the same speed that or current that they are returning back to the battery. So everywhere in this series circuit then, the current is going to be constant all the way through. So if I look at, there's a couple of samples here in the textbook on page 548. On page 5 544 and 545. So let's just flip to our whiteboard here. Sorry, you probably don't want to see that at all. Okay, so let's go to our whiteboard, and sample number 1, which is on page 544, says how much current flows through a hairdryer if 1400 coulombs passes through in 2.25 minutes. How much current? Right? If 1400 coulombs of charge passes through the hairdryer in 2.25 minutes. Right? So I know 2.25 minutes. I know that a minute is 60 seconds. My minutes disappear, and this turns into 120, 135 seconds. Okay, and now I can find my I as quantity of charge that flows through divided by the time that it takes for that to happen. So I can solve my I now, which is Q, the quantity of charge, 1400 coulombs, divided by the time of 135 seconds, and I'm getting a current of 10.4. Notice that the units here are in coulombs over seconds, so coulombs per second, or 10.4 amps. Okay, so that's the speed that the electrons are flowing through that circuit, through the hairdryer. Okay, if I move down to sample number 2, sample number 2 says a nightlight uses 7 watts, with a 7 watt light bulb draws 6.0 times 10 to the minus 2 amps of current. How much charge passes through the bulb in 8 hours? So I'm seeing a number of pieces of information here. So let's say, what am I looking for? How much charge passes through the bulb? Okay, so I'm looking for the amount of charge. Right, Q, quantity of charge. We're told that it's a 7 watt light bulb. So we've already talked about power before. We are told that it runs for 8 hours. And we're told that the quantity of charge is quantity of current is 6.0 times 10 to the minus 2 amps. Now we know that I equals Q over T. So Q is going to be equal to I times T. What about power? We didn't need the power for this question. I do need the current, 6.0 times 10 to the minus 2 amps, coulombs per second, so the time has to be in seconds. I remember from chapters 1 and 2, as much as I might not want to, that 1 hour is equal to 3,600 seconds. Right, and my hours cancel. So 8 times 3,600 seconds is 2880 seconds. And now I can solve for my Q. It's equal to I, that's T, times I, 6.0 times 10 to the negative 2 amps. And a Q that I'm getting is 1.7 times 10 to the power of 2 coulombs. Okay, so there's sample 2, and then sample 3 from the same page. It says how many electrons have passed through with the same nightlight, and it reminds us that the charge on an electron is 1.602 times 10 to the negative 19. So now, question 3 is asking how many electrons? Right, now remember, from chapter 15, right, again, the only thing I said you need to remember from chapter 15 is this one formula here. Oops. Is this one formula here. Q equals N times E. So N is equal to Q divided by E. Okay, the textbook, this question actually reminds us the value for E, which is 6.02. No, it's not. It's 1.602. 1.602 times 10 to the negative 16th, 10 to the negative 19th coulombs. And Q here, we calculated in the previous question, it was 1.7 times 10 to the 2 coulombs. So I can find N now by taking my Q, 1.7 times 10 to the 2, which is Q divided by my elementary charge, 1.602 times 10 to the negative 19th, and I get N is equal to 1.1 times 10 to the power of 22 electrons. Okay, so notice that we've kind of thrown a little bit more at you in that question. All right. Okay, so where are my notes for chapter 16? They're there. Okay, so those are the 3 samples on page 544 and 545. I'm going to leave you with the 2 questions on 548 and 2 more on 575. Now, I'm not done yet. Before I leave you, I want to talk about what direction electricity is moving. Because if I look back at my circuit here, notice that I've shown that the electrons have a definite direction through this path, away from that negative terminal and towards a positive terminal. Right? They're pushed away from negative because like charges repel. They're pulled towards positive because the negative electrons are pulled towards the positive charge electrode because opposite charges attract. Okay, so historically, what we understood about electricity was that electricity talks about the movement of charged particles. Right? And that's what we believed, and today we still believe that electricity is about current or the flow of charged particles. What they kind of got wrong was what are the charged particles? They believed back then that the charged particles that were moving were positive particles moving. Right? Now, they had no real grounds to think that positives were moving. But we now know that that's not right, right? What we know is that what's moving here, today, we know that the moving charged particles are electrons. Now, it turns out that what they were talking about in terms of the movement of positive particles wasn't 100% wrong, right? Because we think, well, how can it be the movement of positives and the movement of negatives? Because the positives would have to move in the opposite direction. Right, the positives would have to be moving away from the positive. Let's make this bigger here. If I was talking positive particles here, can I get a different color? They would be going this way because they would want to leave the positive terminal and be pulled towards the negative terminal, and they would flow this way. So that is totally contradictory, or opposite to what we're looking at when we say electrons are moving or negatives are moving. Now, what really, so chemists or physicists basically talk about a type of flow which is the flow of positive from the positive terminal of our source to the negative terminal of our source, and we call that conventional current. Convention means what we've always done, right? Convention says red means stop and green means go, right? That's the convention. That's what we all know. That's what we all believe. My 4-year-old grandson would tell you, red means stop, Papa, the light's green, right? So that conventional current still works. And you think, okay, again, that doesn't make any sense to say negatives are moving and positives are moving in a current. Well, if you think about it for a minute, if a positive charge, let's go with a different color here. Let's go with, say, green. If I start with a positive charge here, right, this particle right here is an electron right here. Okay, there's an electron right there. Okay, and the electron that's sitting right here is going to move onto the positive terminal. What that does is it creates a positive space where that green dot is. Now with the green dot, it's going to attract electrons. It can't pull them back from the positive terminal here. So what it's going to do is it's going to take the next electron in the way and pull it down. So an electron from here is going to move down, and it's going to create a positive space where that next dot is. Okay, maybe you're getting the idea here. So there's a negative there, and it's basically the one below it is getting pulled towards a positive electrode, but it's positive. It wants an electron, so it's going to take the electron from here, and this electron is going to move here. Notice what the direction the green dots are going. Right? The green dots are moving in the same direction as the red arrow. They're moving from positive to negative. The green dots aren't positive particles. The green dots are positive spaces. And what happens is, as the negatives flow, as the electrons flow through the circuit from negative to positive, they create positive spaces along the way that move in the opposite direction. Right? They're going to move in the opposite direction until ultimately the positive spaces end up back at the negative terminal. So this whole concept of a conventional current that says positives are moving, isn't totally ridiculous. It's wrong, but it's only wrong if we say that positive particles are moving. Right? So the particles that are actually moving are the electrons, which are negative, but that positive motion still does exist, and we can call that the conventional current. Now you'll see that this gets confusing because when we get to later parts of this chapter, we'll see that there are places where some physicists in the world are talking about current in terms of conventional current, and some physicists in the world are talking about current in terms of electron flow. And they're opposite to each other, but all the math works. It doesn't matter whether you got the math going clockwise or counterclockwise in the circuit. The calculations all still work the same, and all the math works either way. So it doesn't matter how we do it. Now, ultimately, we've already looked at in Chapter 15 the concepts of conductors and insulators based upon the fact that atoms have electrons and atoms have varying degrees of attraction or hold on their electrons. Those that will not electrons leave are conductors. Those that gladly let electrons go into them and come out of them are insulators. Vice versa. Those that are holding on to their electrons tightly are insulators, and those that allow electrons to flow through them are conductors. Now, what decides whether something will be a conductor or an insulator to some degree depends on the nucleus. Right? And we're not going to talk too much about the nucleus here because you're probably tired of talking about the nucleus. And we are concerned about electrons. Right? But the nucleus basically impacts on how elements become, or matter becomes, either a conductor or an insulator. So again, from Chapter 15, we know that conductors are those that have loosely held electrons, they can be pushed out of an atom, and then they will be replaced by incoming electrons. Now, a lot of the elements that we know are good conductors are metals, because metals have got a small number of valence electrons, and because of that, they're happy to let them go, but then they're also happy to accept more electrons too. And again, we talked a little bit more about why metals are good conductors later on in this unit. Okay, the other type of matter are insulators, and like I said, they're holding very tightly to their electrons, and therefore they will not accept new electrons and will not allow electrons to flow through them. Right? And again, a lot of our nonmetals are insulators, and a lot of organic compounds that we've been talking about in organic unit, in my chemistry course, are good insulators too. They hold onto their electrons very tightly. It includes a lot of the plastics and the rubber material that we use to coat electrical wires, so that you can handle electrical wires without getting a shock. Now, just to complicate things a little bit more, we've got two possible types of electric circuits that were developed by two brilliant physicists, Nikola Tesla and Thomas Edison. Now, going back to the beginning of the 20th century, around 1910 or so, if I remember correctly, we've got Nikola Tesla and Thomas Edison have both developed different ways of generating electricity, right? And Thomas Edison came up with a model that says, here is Niagara Falls, here is your house. Electrons are going to flow from Niagara Falls to your house, deliver energy, go back to Niagara Falls, pick up more energy, go back to your house, deliver energy, go back to Niagara Falls and pick up energy, right? And according to Thomas Edison, electrons would only have one direction, right? That's why he called his electricity direct current, right? Direct current means electrons only have one direction, right? And that's how he wanted to deliver electricity to your house. Nikola Tesla had a slightly different idea. Nikola Tesla said, I'm going to send electricity from Niagara Falls to your house and back again, and to your house and back again, and to your house and back again. I'm going to send it forward and backwards, forward and backwards, and forward and backwards, and it's actually going to change direction 60 times per second. Right? Now, that number 60 hadn't arisen yet, but that's what you have in your house today. You have electricity coming and going through the two prongs of your plug. So if you've got a plug in your house, say your charger for your iPad, you're going to plug it into the wall, and then electrons are going to come in. They're going to go through your device and come out this side. Then a 60th of a second later, they're going to change directions, and they're going to basically go back this way and come out this way. Then they're going to 60th of a second later, they're going to change and go back this way, come back this way. So they're constantly going back and forth through the two prongs of your plug. We're not going to talk about the ground pin right now, just talk about the two live prongs. Right? So electrons are going to go back and forth, back and forth, back and forth. That was Nikola Tesla's version of electricity called alternating current, where electrons alternate their direction, right, back and forth, and we can see who won, right? Nikola Tesla won the battle. At this point in time, right, in the history of the world, houses did not have electricity, right? Nobody's house had electricity. Schools, stores, factories, no electricity, farms, anywhere. So who was going to win this would basically change the world, right? Because we were going to deliver electricity to every home on the planet, every business on the planet, every place on the planet was going to get electricity delivered to it, right? And it was either going to come in an alternating form or in a direct current form. And this was a huge, huge fight, right, between these two very brilliant physicists. And ultimately, like I said, Nikola Tesla won. So we've got AC electricity, where electrons have alternating direction, alternating current, and DC electricity, where the electrons flow in one direction only. Now, for my charger for my laptop, I've got, oops, the plug here. Then I've got a little rectangular box here, and then it plugs into the laptop down here. Okay. Now, what's happening at the very beginning here in my plug is electrons have alternating current. Right? They go in one side and come out the other. They go in that side, they come back out the other. They're alternating back and forth. Pick up energy, deliver it. Pick up energy, deliver it. Pick up energy, deliver it. Okay, so there's what's happening in there. And it's going to send that electricity in alternating currents along this wire, back and forth, to the transformer, which is what this is, to the transformer and back. What the transformer does is it takes the alternating current that's coming from the plug and it changes it to direct current to go into my laptop. My laptop needs electrons to flow in one way and flow back to the transformer, and then forward again, and then back again, and then forward again and back again in one direction only. So on this side of the transformer, I have AC electricity. On this side of the transformer, I have DC electricity. And the purpose of that transformer, one of the two purposes, is to change AC electricity into DC electricity. Now, think about your cell phone for a minute. Your cell phone has a battery in it. And coming out of the battery, again, I'm just pretend it's this kind of battery. It's not. But if it was this kind of battery, electrons are going to flow in one direction only, right? So in your cell phone, electrons move in only one direction. In the battery of my laptop here, electrons move only one direction, right? There's a battery in there. Batteries only provide direct current. So in order to charge the battery for my laptop, which provides one directional flow, I need to charge it in one direction, right? Not the band. And that one direction is going to charge in the reverse polarity. It's going to charge the battery for that laptop, and then ultimately I will have the DC power that I need to run the laptop. Right? But I have to change the AC electricity from Nikola Tesla into DC electricity of Thomas Edison in order to make that that laptop work. Any battery-operated device. Okay, now we're going to talk about why did Nikola Tesla win. I mean, before in this point in your life, I mean, we all know Nikola Tesla a little bit now because we've named that major street in Hamilton after Nikola Tesla Boulevard. But I think everyone probably knew Thomas Edison long before we heard of Nikola Tesla. I think, well, why is that? Because Thomas Edison had so many great discoveries. Nikola Tesla changed the world, right? Absolutely. He's got alternating current electricity that is used everywhere on the planet. Right, so I mean, he's somebody we should all know, and again, we'll talk about why he won. We'll talk about why Tesla won, because of its ability to transport over long distances. Again, if electricity is made at Niagara Falls, some of it goes to my mom's house in Sudbury, some of it goes to Ottawa, some of it goes down to London, Ontario, some of it goes into New York City from Niagara Falls. So some of those are huge distance, maybe up to Thunder Bay, right, which is a 15-hour drive. Electricity's got to travel a long way. It turns out AC electricity travels better, right? And we're going to talk about why that is. But if we're going to have to travel it across or move it, transport it across a province, across a country, long distances, we need one that's going to transport well. Now, from grade 9, just very quickly, I want to review what we know about electricity. Okay, so we know that for electricity to flow, we need a closed circuit. Right? The closed circuit is a path, right? And it needs to be a complete path with a few main parts. Number one, I need to have a source. There's 4 parts. I need a source, which is where electrons get their electrical energy from. Right? The electrons, the source contains another form of energy that's going to convert that energy into electrical energy. Maybe it's chemical energy in a battery, and that's going to be used to make electrical energy. Maybe it's kinetic energy in a wind turbine, and that's going to give electrons energy. Right? Maybe it's a solar cell, and it's capturing radiant energy from the sun, and it's going to give that energy to the electrons. Whatever the source, right, electrons are going to be entering into my circuit with energy that they got from somewhere else. Then I need a load. A load is something that's going to use that electrical energy. Right? It's going to use that electrical energy. My phone is a load. My laptop is a load. A TV is a load. A stove is a load. A fridge is a load. Anything that plugs in or uses a battery is a load. So anything that uses electrical energy and converts that energy into something else, a flashlight is a load. Right? And basically what's going to happen is the load converts the energy of electrons into some other type of energy, right? Which is why we bought the device in the first place. For the electrons to move from the source to the load and back, I need wires or connectors. And then I also need controllers. Controllers are things that will be put in our circuits that can turn the circuit on or off. I can speed up or slow down the rate of electron flow using things like dimmer switches and other more sophisticated pieces of equipment. So, in grade 9, we learned some of the basic symbols that we use for doing circuit diagrams. Right, so there's my cell. The cell has a negative and a positive terminal. Right, a battery is a cell in series. So if I take what I have in my laptop is I can't remember how many volts it is. So my car has a 12-volt battery, so it's got 8 1.5 volt cells. So I've got a cell connected to a second cell, which is beside a third cell. 4, 5, 6, 7, 8. Okay, and as electrons move through the circuit, again, ultimately they're going to come out the negative end and come back to the positive end. Right? Now, as they get from the positive to the negative inside the battery, they have to go through all of those cells, and as they're doing so, they gain energy with every cell that they go through. So when I put those cells together, they're called a battery. Right? So that thing that I was drawing earlier, right, that's not a battery, that's a cell. It's a double A cell, single A, triple A. Right? It's got only one cell. It's got one set of compartments that separate negative from positive. If I've got a DC generator, there's my symbol for a DC generator. The AC alternating current generator has got that squiggly up and down line to show electrons are going in different directions. Our symbols for a resistor are this one here, again, just up and, close, up and down, up and down. There's a resistor. A lamp, there's lots of ways to draw a lamp. The easiest way is what they've got there. It's just a filament with a circle around it. For an electric motor, right, there's our electric motor. We're not going to be using this. We're not going to be using this. We're not going to We will be talking transformers. We'll talk more about them later. And then we need to continue adding a few more parts here. Some of our controllers or some of our devices for doing measurements are an ammeter, which measures the amount of how fast electrons are moving in amps. Something called a voltmeter, which measures the voltage of electrons. In other words, how much energy are they carrying? We're not going to use a galvanometer. And then we also have a few more things. I've got a switch that I can use. Again, remember the knife switch that we had in grade 9? It was on a piece of wood, had a little brass arm that you could drop down to close the circuit or lift to have an open circuit. So there's the open circuit, and there's the closed switch and open switch. Here's our symbol for ground. And then this is our fuse. And again, we're going to talk about fuses a little bit later in the course. So again, just be, I'm going to be using these symbols all the way through the next 2 weeks. So just go back and have another look at them a couple of times, just so you've got a good sense of what they are. I'm going to stop there. We'll leave you with those questions from earlier. A little bit of a longer note here, but I wanted to get through all